That said, and there's also some stuff down at the bottom that I didn't get posted before the script, before I posted it on Blackboard. So when we get down there, you'll just need to type in like 4 lines worth of stuff. But today we're going to be going over the generalized linear model, specifically logistic regression. So the nice thing about the generalized linear model is that it allows us to abandon some of the assumptions that we have to follow with a general linear model. And so logistic regression is what you'll be using, like with categorical outcome variables. As we'll see here in a minute, before when we've had problems with our assumptions, we were able to transform things. So when our dependent variable is reaction time, for instance, we're not expecting a normal distribution of outcomes, like it's going to be skewed. Like most people, reaction times will be there in the milliseconds, but you'll have that one person who wasn't paying attention and was like, oh, click. And so there's a 3-second reaction time. And, so it's not going to be normally distributed. And so, but if you, for instance, log transform that outcome, that now the log of that, resembles a normal distribution. And so this is conceptually similar to that. But as you'll see here in a minute, that it can't actually be directly transformed in that way, which is why we end up converting things to odds and log odds and things like that instead of transforming the specific variables. In these transformations, those, like you'll see them referred to as the links. Like depending on which link you're using, that will transform it one way or the other. And so you just have to be aware. When he talked about you have your probability space, your odds space, and your logit space, or the log odds space. And just remember that you can convert from one of these to any of the others with that flow chart of to convert from probability to odds. You do this. Convert from odds to log odds, you just take the log, then you exponentiate to go from log odds back to odds, and then you can convert that back to probability. But you just have to be cognizant of which space you're in or which space you want to be in, depending on the specific analysis, or in the case of like homework or an exam, like what it tells you to interpret it in terms of odds or in terms of probability or in terms of log odds and things like that. So you just have to remember which space you're operating in and think about which space you either need to be operating in as per what the question says, or in the case of just like, real world research, like which one is, most interpretable or most meaningful to the analysis that you're trying to do. So we're going to start using this Mraz data. And what this is it's about women participating in the workforce. And so we have several variables here. LFP is whether or not they are participating in the workforce. So that's going to be our outcome variable. K5 is the number of kids 5 or younger that they have. K618 is the number of kids between 6 and 18. And then they also have age in years, a dichotomous, whether or not the wife attended college, whether or not the husband attended college. The log expected wage rate. And here they talk about if like all of these observations are the women themselves. And so if they're in the workforce, then LWG is their actual income. If they're not, then it was imputed. And we hadn't talked about missing data and imputation yet this semester. So in 1 minute or less, what that means for the imputed values is that if you take all the people who do have an actual wage, and then you create a linear model to say, okay, so if I predict this variable based on whether or not the husband was in college, whether or not the wife is in college, what their age are, and how many kids they are. Like, what's the prediction that will minimize error here? And you form a linear model, and then you take that linear model and you apply it to people who don't have the things, and basically predict what that variable is based on all the other variables. So that's what this imputation is. And so that's what that'll be. And then the I and C is the family's income exclusive of the wife's. Blah, 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 exploring the data. So here I'm just pointing out that some chart correlation doesn't handle factors. It only handles numeric things. So what this lapply stuff does, this is lapply is list apply. And basically a data frame is just a list of lists, that each column is a list, some vector of information that you just put them all together. So by using lapply, I put in the data frame and then the function as numeric. What lapply will do is apply whatever function you put in across whatever list you put in. In this case, it's saying to take the data frame and for each column, apply the function as numeric. But lapply outputs lists instead of a data frame. So if we look at it here, you can see, here's first list, LFP, and then here's the second list and the next one. So once you wrap that in data frame, it will convert everything to numeric and output a data frame. So that's what I've plugged here into chart correlation, so that when we look at that, we're able to look at our descriptives and correlations, blah, blah, blah. Yeah, no. Yeah, that was just for the sake of being able to throw it into chart correlation, so that even if I'm not looking at like the actual correlations and stuff of like some of those dichotomous variables, like at least lets me quickly eyeball the distributions and things like that, those univariate distributions, and then look at the bivariate distributions of the relevant variables that I care about and stuff like that. So it's just kind of a shortcut to getting that information that I wanted to, instead of just sitting here and saying to leave out these other variables and then having to go in and look and see, well, what were the cell counts for these dichotomous things and blah, blah, blah. So let's say that we believe, which is not a terribly shocking belief, that the number of kids under 5 that a woman has is related to whether or not she's participating in the workforce. Before today, we would, the analysis would be a linear model. So here I'm just creating a numeric outcome for the labor force participation, subtracting 1, because as you saw before, it was actually 1s and 2s instead of 0s and 1s. So I just want to change it to 0s and 1s. And then we fit our linear model and we regress labor force participation on the number of kids under 5. And we see, yep, there's a significant relationship between the number of kids under 5 and whether or not somebody participates in the workforce. Where the problems come in is where, like, if we check our assumptions on this model. So first we look at our normality, and as you can see, we don't have normally distributed errors here, but that makes sense because there's only 2 possible outcomes. So it's not like a 7-point Likert scale where you're expecting a bunch in the middle and then fewer as you taper out. Like, there's only 2 possible outcomes, so you would expect a bimodal peak of errors. Then when we look at our constant variance, this is the one where what we would expect is to see over here, evenly scattered along that line. This is one where you don't want to see that funnel shape and things like that. But if you think conceptually about what this is telling you, if it's looking at the residual, some predicted value against the actual value, but the actual values are all only either 0 or 1. So in some cases, the predicted value will be 0 and the actual value is 0. In some cases, the predicted value will be 1 and the actual value is 1. But where it's predicting 5, no data points actually have an actual value of 5. So there in the middle, everything is going to have some amount of error. And so it kind of makes intuitive sense that when you have a dichotomous outcome, you don't have, you don't have homogeneous variance across your predictions. So that's no good. And then when we look at our linear plot, again, like that just doesn't really particularly look like it makes sense or, what any of our plots have seen before. So if we just look at this jittered scatter plot, like you can see that, like even here, you can kind of visualize and see that there does seem to be a relationship between the number of kids that they have and whether or not they participated in the workforce or not. I mean, you can see that as the number of kids goes up, you have more dots down here and did not participate than you do up there and did participate. But there's a big disconnect between those two things. It's not that gradual thing. It doesn't look like a scatter plot. And so again, before we transformed variables when this was a problem, but we can't really directly transform this data in any way to take care of those assumptions. But with logistic regression instead, we do this with transformed probabilities instead of looking at the errors. So if we want our predictors to have that linear relationship, there's a problem with using probabilities because probability is bounded by both 0 and 1. But if you recall, he talked about as you move from one space to the next. So down here, all I'm doing is creating a data frame where I have a sequence of probabilities from 0.01 to 0.99, and then also calculating the odds for each of those probabilities, because the odds is just probability divided by 1 minus probability. And so when we create this data frame and then look at our plot, so this is our probability and the odds. And now your odds are still bounded by 0 on the low end, but they're not bounded on this upper end. You can have 10 to 1 odds, 100 to 1 odds, 11 billion to 1 odds. It's infinite. But it is bounded by 0 on the low end. But we can fix that by instead converting it to log odds. So here, all I'm doing is I'm taking that same data frame and that odds variable that we computed and taking the log of those odds to create log odds and plotting that same thing. And now we're no longer bounded by 0 and 1. There are some other links besides the logit. You may see in manuscripts somebody talking about like a probit model or some other types of links. We're not going to talk about those. But here under family, if you look under, when you specify in your GLM which family you're going to use. In our case, we'll be using the binomial family, and the default is logit. So if you just enter family equals binomial, you can leave out the logit part because that's the default. And unless you put something else in, it assumes that that's what it is. But down here, it talks about the logit, probit, cotchit, and these other types of links for that binomial family. And again, not going to get into it because we won't be using it, but I just wanted you to at least know that if ever you do need to look into what these other types of things are, just remember to look here, and it'll tell you what the different types of links are depending on what family you're using. And so as far as fitting the generalized linear model, it's incredibly similar to just the general linear model. The only difference is that you have to tell it what family of error distribution you're looking at. In our case, it's binomial error distribution. So instead of using LM, we have GLM up here as the function. And then we add family equals binomial, and we run this model. And we'll compare that with the model that we ran earlier. So the first thing to notice is that your parameter estimates. So this top model is our logistic regression, and this one down here is just the linear regression that we fit earlier. So you'll notice that your parameter estimates are different. But another thing is that you'll notice that when we do this logistic regression, we don't have residual standard error, and we don't have R squared, because we're not working with errors anymore. Like now we're working with this thing called deviance. And that goes back to what we discussed earlier as far as like if your predicted value is 0.5, like it's all error there. You can't actually have that actual value. It doesn't exist. And so error as we have known it up to this point just doesn't make sense in terms of a logistic regression. And so, again, like instead of using sum of squared errors and ordinary least squares, we're working with the maximum likelihood estimation that Patrick talked about on Wednesday. So a function of probabilities rather than the errors themselves. And then in terms of the interpretations, whereas before when we're running our linear model, we're talking in terms of raw units. So, a 1 unit increase on X is associated with a 3 unit increase on Y. But just remember that whenever we're working with this logistic regression, we're not working in raw units, we're working in log odds. So just the standard output here that we're looking at is telling you in log odds what are the differences here. So where K5 equals 0, the intercept here, the average, the log odds are 0.48 that a woman is participating in the workforce. And then as the number of children under 5 goes up by 1, we expect a decrease in the log odds of 0.87. Now, if log odds seems weird and not particularly interpretable, that's not surprising. But in order to switch from log odds to odds, all you have to do is exponentiate it. And so if you wrap it in this EXP and get your coefficients, now we have our odds of the same thing. So this is telling us, again, our intercept is the average when everything else in the model is 0, just like all the other regressions we've done. And so for a woman with no kids under 5, the odds are 1.6 to 1 that she's participating in the workforce. So it's more likely than not that she is participating in the workforce. But as we move up and she has one kid under 5, those odds go down by 0.42, basically. Now I say down, even though there's not a negative here, because remember when we're working in odds, there are no negatives here. It's bounded by 0. What's up? Right here? The log odds of a woman with no children participating in the workforce, and then the change in log odds of a woman participating in the workforce when she has one kid under 5. Yeah, by a factor of log odds decrease by 0.87.
So that 0.48 is the maximum likelihood ratio, right? I remember Patrick saying that.
We'll get to that. That's coming up here once we scroll down just a little bit further. This one. So now we're talking about odds instead of log odds. This is just, and if you take this and wrap 1.616 blah 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 like log of that, it will give you that what the intercept was of the other. So that's all we're doing is we are taking it out of its log form. So here, now our interpretation is the odds are 1.6 to 1 that a woman with no kids under 5 is participating in the workforce. When number of kids under 5 goes up by 1 unit, we are expecting it to change by a factor of like 0.42. So instead of the odds being 1.6, the odds are 1.2. 1.2 to 1. So it's still with one kid, it's still more likely than not that she's participating in the workforce. And if we look at we go back to our jitter plot, it might help make some more sense. So by and large, the odds are 1.6 to 1. Somebody with no kids is in the workforce. There's a lot more up here than there is down here. When you move up to having one kid, the odds are still slightly, better than not that she's in the workforce because, the odds are still 1.2-ish to 1, but almost a 50-50, odds here. And then as you go up another kid, those odds will decrease again by 0.4. So now we're looking at 0.8 to 1. So once they have 2 kids, it's more likely that they're not in the workforce than they are.
Say that. You know that it goes down in this case.
Because when you look at the log odds, like that will give you the sign.
So that's the relationship.
Yeah, because your odds are going to be bounded on the lower end by 0. You can't have negative odds. 1 to 1 is even odds. If it's smaller than 1, you get 0.5 to 1. 0.1 to 1, 0.000000001 to 1, but not 0, and certainly not negative. And then if it's bigger than 1, 2 to 1, 5 to 1, 10 to 1, but it's bounded by 0 on that lower end. So if the odds are lower than 1, then it's likely to go this way. But if it's higher than 1, then it's more than likely to go, the other.
Whatever the sign for your
Interpretively, yeah. That's how you would know if you can't make just intuitive sense out of it. That it makes sense that their odds aren't increasing to be in the workforce as they have more, infant and toddler children. And so for the likelihood ratio test, to get to what you were saying earlier, that's where you're going to wrap this in ANOVA. And this test is distributed on the chi-square distribution. But for the chi-square test, it only uses the degrees of freedom for the parameter that's being tested itself. As far as where it says type equals 3, we didn't really talk about types of sums of squared errors last semester because we didn't talk about ANOVAs, which is nice. There are 3 primary types of sum of squares, but I think there's actually 5 types of SS. Weird. And when it comes to the type of sum of squares, just full disclosure, that is one of the things I cannot tell you off the top of my head. I can't remember what's what. It has to do with how and when and what variance gets partialed as you look across different variables. So depending on how many predictors you have, the different types of sum of squares can all be identical and not change at all. But as you have additional things like which overlapped variance is and isn't attributed to the numerator versus the denominator, MSs and stuff like that, is where the types of sum of squares come into play. But suffice it to say, the default is type 3 sum of squares. If you're working on SPSS, it will automatically give you type 3 sum of squared errors. Frustratingly, with R, a couple of the built-in ANOVA functions default to type 2 sum of squares for some reason. But when you use this ANOVA function, which is actually from the CAR package, you can specify what type of sum of squares you're going to use. And so just all you really need to remember is that you're always looking for type 3 sum of squares, basically, at least certainly for the purposes of this class. If ever you're working with ANOVA, you're going to use type 3 sum of squared errors. And so here is, basically conceptually where deviance is conceptually analogous to error as far as what we're comparing between a null and compact model. You can kind of think of this as a test of that null versus compact model in terms of those likelihood ratios. So comparing is the bang for the buck there that including this parameter changes that deviance enough that it's significant and it's a substantially better estimate or not. So as far as plotting this goes, this week I'm only going to cover plotting the probability plots, which is the only one, if you remember, that in those 3 spaces, when you're in your probability space, you still have your raw data, but once you transform from probability space into odds and log odds space, you no longer have the raw data. You can't plot raw data on this transformed thing. So for this week, all we're going to talk about is plotting that probability thing. Probably next week, we'll go ahead and talk about how to model so that you can show, the odds or log odds and the differences as a function of some variable. But for this week, we're just going to stick with this one. Graphing it is pretty well straightforward, and it's nothing that we haven't done before. For now, I'm actually going back to the original way we learned to manually plot models instead of using ggpredict. I haven't figured out yet how or if it's possible for ggpredict to play nice and give you, logistic regression predictions or not. If you can, I just haven't figured it out yet. But you can use, if you recall, at the beginning, we learned to use the predict function where you say predict a model, some new data frame that you want to predict the values of. And then, when you bind that with the original data frame of the values that you're trying to predict, you can create, the plot data frame. So we're going to be doing that. But instead of using predict LM, we're going to be using predict GLM. And so for the only things that are really going to be different in this, for one, we have to include this the type. So when we look in our type, it'll tell you for type equals response, it's going to give you, it's on the scale of the response variable, which in this case, our response variable is probability. So when we're looking for the probability plots, we tell predict GLM that type equals response, and that's how what it will output is the predictions of probabilities. And also, unlike ggpredict, one of the things that I don't like as much about just using the predict family of functions is that you have to include this SE fit equals true. That's how you get it to output your standard errors. But note that it's standard errors, not the confidence intervals like ggfx puts out. Now, standard error is only a transformation away from being confidence intervals, but I personally like confidence intervals because I think a lot more people are getting to where they kind of intuitively understand and they're expecting 95% CIs instead of standard errors. And it's almost as if, some people, if you said like, Schoner, the standard errors, they would be like, wait, what? Where's the confidence interval? And be like, well, multiply it by 1.96 and you have your confidence interval. But like as academics, our jobs is to make it as easy as possible to the reader to soak up the information we're trying to give them. And so I like confidence intervals. But all you have to do is multiply a standard error by 1.96 and you now have a confidence interval. So that said, we start by making a data frame. And it's just a sequence, in this case, from 0 to 3 by 0.1. 0 to 3 because that's the min and max of this particular thing, but this is no different than saying, max df k5. Oops, that should be min. From there to max df k5 by 0.1, and it will give us the same thing. That now we just have our sequence of values that we want to make predictions for, because we want to make predictions all the way across this x-axis. We want some prediction and some standard error for each of those points. Mm-hmm.
So first thing in my drill here, I have expand.grid.
Oh yeah, so that's the other thing. In this particular case, I've changed it to data frame because there's only one variable in this particular prediction. Expand.grid does the same thing as, like, it makes a data frame, but whatever you put in there, it will output every combination of those. So if, for instance, you did have two variables, and so you have K5 and WC for whether or not the wife was in college, and that dichotomous yes or no, then what it would do is it would produce all these values of K5 in a second column that's WC, that's yes all the way down. And then all of these values again with no. So that expand grid is just, if you do have multiple factors that you need predictions on, then you need every combination of those different variables to predict what's my value when K5 is 2.2 and WC is no? What is it when K5 is 2.2 and WC is yes? And so I had put that in there initially just to remind you, especially like for the homework, you will be working with multiple factors. And so if you just do, data frame, K5 equals whatever, and something else equals whatever, it's not going to give you those multiple combinations of things.
So secondly, why are we not using K5 equals 4?
What?
Why are we not using K5 equals 4 and 5 there on the x-axis? Why are we only going from 0 to 3?
Because we're only making predictions based on our data. Our data only goes up to 3, and it doesn't have more.
So no wonder 4 to 4 and 5.
Yeah, no. I mean, if you remember that, like the standard errors or confidence intervals that you're predicting how, they get really, really big as data gets smaller and smaller. And so up here, there's no data. So, there's a lot of error up there. And you at least in this particular case, we're not trying to make predictions outside of our data.
So that leads into another question where, I guess then for our predictor variable, where we need to know our range.
Not if you set it up by min and max like this, which is, how we've done it. If you look back at last semester's drills, that's almost exclusively I used like min and max to be able to define those things. Because then, but in this case, I didn't, just because I already had this graph pulled up and I saw that like, 0 and 3 is the min and max, and like 0.1 is a good thing. If this predictor variable is 0 to 100, you're probably not gonna want to go by 0.1s. If anything, you'll do just a sequence from 0 to 100 by 1s. And so, whenever you're looking at this, just think of in terms of like, what is going to divide this axis up into lots of little chunks? Because basically what we're doing is we are just making, if we only make one prediction per line, if we went up by 1s, it would give us a prediction here, a prediction here, a prediction here, and a prediction here. So it's going to be, when you create a line between these points, it's not going to be like a curved, smooth line. But if instead you divide this axis up into 100 different points, then now we're connecting this dot to this dot, this dot to this dot, this dot to this dot, and that's what gives it that appearance of having a smooth curve. So the biggest thing when you're looking at setting up this initial data frame for your predictions is just thinking about like, at what level do I need to divide this x-axis up into small chunks so that I don't have, jagged lines between these predictions. And so then, just like we did before, except for whereas before we just used predict LM, now we're using predict GLM. And if I just run this section of it here without running the whole line, it gives us our fit, like our predicted value and that standard error. But that's not usable in that form because it's not in a data frame, which is why we wrap that and C-bind it with the original plot data frame. So now when we look at our plot data frame, we have for where K5 is 0, our predicted value is 0.61, our standard error is 0.01. If we had multiple variables, then we'd have an extra column. So it may say K5 is 0, HC equals no. What's the fitted value? What's the standard error? Go all the way down, and then below all these, it would be like for K5 of 0 when HC is yes. What's the predicted value? What's the standard error? So then we have that same setup that we are familiar with from using ggpredict. And then from there, everything is set up the same. So running this bit by bit, here's like basically the same jittered plot that I made earlier. if we add this next line where now we just say from the plot data frame, X is K5, Y is fit, we now have our prediction line here. And then here we say, all right, now add on another line from the plot DF where X is K5, which K5 is that sequence from 0 to 3 by 0.1. And where our Y is the fit, that prediction line, plus 1.96 times the standard error, gives us that upper 95% confidence interval. And when we run the whole thing now, we also have, we add on that lower, it's Y is fit minus 1.96 times the standard error. So if you don't want the confidence intervals, if you just want to plot your standard error, then you just don't need this. It would just be fit plus standard error of fit, and fit minus the standard error of fit. But by multiplying it by 1.96, we're converting that standard error to our 95% confidence interval. And so as far as this type of plot goes, there is a plot, maybe two on the homework. But you know, it'll follow this same process. But one of the nice things about learning everything through the general linear model instead of ANOVAs and things like that, now that we're switching over to the generalized linear model, a lot of things work the same way as far as, you know, multiple variables and, you know, whether or not they're interacting. The only thing that changes as far as the output is not having the error. But as far as the interpretations, you know, just thinking about what units are we in? Are we talking about log odds? Are we talking about probabilities? Things like that. But as far as fitting the model, it works the same as it always has. So in the homework this week, you know, it'll be the same data set, but it will tell you, like, based on this other variable or the interaction of these two variables. So again, if you have multiple variables and it says to, you know, plot separate prediction lines for, you know, plus or minus 1 standard deviation of some variable, then all you have to do is put that up here. And so if it's plus or minus 1 standard deviation of variable X, then in expand grid, you add the same K5, and you add your X equals, and you compute whatever plus and minus 1 standard deviation is. And so then it will give you all your predictions for each. And then when you get down here into your plots, all you have to do is remember to here add your grouping thing. So group equals whatever that variable is called in your plot data frame. That's going to tell you, like, these are two separate lines, so you don't just get that zigzag line thing. And then you can also, you know, add your colors to things. So one prediction line is one color, one is another. Yeah, so as far as fitting the model itself, there's nothing new to learn. It's exactly what we've been doing all semester. Whether or not you have an interactive model or an additive model, all that sort of stuff conceptually maps onto the generalized linear model the exact same way. Like the fundamental difference between the two is how are your errors distributed. And in this case, we are freeing ourselves from the need for normally distributed errors. And instead we're saying we have binomial errors. And nested error structures, multi-level models. I think we might actually be getting into multi-level models later this semester, at least like a brief unit, although like that's an entire different class really. And so, you know, there will be time for all that sort of stuff. This is the section, if you, y'all should add this to your script because I added this after I posted the script to Blackboard. But basically what I want to point out here is a few things. One, just remember that You need to be thinking about which space you should be in, whether that's determined by if the homework or the exam says to interpret it in terms of probability or interpret it in terms of odds or whatever. You have to think about what output am I looking at. So whenever you just run, the regular model is going to give you your log odds. If you exponentiate it, you turn it into odds, and then you can go back and turn that into probability mathematically, or you can do it using predict. But so as far as like last semester when we talked about like point estimates and stuff, so for like this specific value, what would the prediction be? You can use predict to tell you that. So if I want to predict what are the log odds of a woman with 3 kids under 5 participating in the workforce, I just predict from that model, and I predict it on a new data frame where there's only one value of K5, and it's 3. And so when I run this line, the log odds of a woman with 3 kids under 5 participating in the workforce are negative 2.13, 2.14. If I want that in terms of odds, I can exponentiate those log odds, and the odds of a woman with 3 kids under 5 participating in the workforce is 0.12 to 1. So by a long shot, it's less likely that she is participating than it is that she is participating. And as far as taking that to probability, if you use that predict and you put that type equals response, now that's how you tell it that like I want this output in terms of probability. Just like we did here, where we were wanting to predict, like this is our probability prediction. And so when we use that type equals response, the prediction that it puts out is this probability. So in this case, we're telling you to put out the prediction of the probability, but only for this one specific value of K5. From that, you can expand out. If we had 2 variables, 2 predictors in this model, and we wanted to predict, a woman with 2 kids under 5 whose husband did go to college, then, data frame K5 equals 2, and then HC equals yes, that sort of thing. So you just have to tell it in your data frame, like, it has to have all of the predictors that are in whatever model you're trying to model and predict from. But as long as you put those in that data frame, like all you have to do is plug in which values of these variables are you wanting to get a prediction for. And so if mod G here did have K5 and WC, whether or not the wife went to college, I could tell it for 1 kid and the wife did go to college, so WC equals yes. Whatever it's looking for, like you can use that to get out your specific predictions. And if you're wanting a probability, you can tell it type equals response to put out that probability prediction. Otherwise, it'll put out your log odds prediction, but you can then exponentiate that if you want to convert your log odds to odds, and things like that. So I don't think that the homework this week I certainly don't think that it'll be hard, because it's basically going back to conceptually, like the process is the same as saying like, fit a linear model and interpret this estimate. Like the biggest thing is just stopping to think about what space are you in. So how am I talking about this? This is the average log odds, or if I want to convert that to the odds or whatever the case may be. And then remembering, using this type of stuff for your plotting. If you're plotting interactions, you need to use that expand grid instead of data frames so that you can generate the predictions for every level of every combination of all the predictors. that sort of stuff. And Patrick is adding a philosophy of science question or two to the exam. So it'll be this afternoon before I get it posted, earliest. I'm not sure when Patrick's planning on getting the exams back to you. We have a student that needed an extension for reasons, and so there's still an exam out currently. So I don't want to talk about it and whatnot. But if you have any specific questions about the exam, you can always email me, and now that it's over, I can answer questions. I think the biggest thing that kind of threw people off was the graphing stuff, especially on that second one. But I think it was more than anything kind of confusion that was on mine and Patrick's end, that the something that he had said was different than something that I had said, and like both ways can work, but it just depends on what specifically you're trying to plot, which is why I then sent out that email on Wednesday trying to clarify, like, just remember, there's multiple ways you can do this, whether you're putting the continuous thing down here with the prediction lines, or if you're putting the groups on the x-axis with those vertical jitter plots, dot plots. And because I think that was one thing that was, I saw some who were trying to put, they had the continuous variable on the x, but they were trying to put the vertical dot plots instead of the regression lines by group sort of thing. And so that did cause a little bit of confusion there. But so far as like the real meat of the exam, it seems like most people were able to get the contrast stuff under control.
Question, I got a little lost.
Mm-hmm.